Let us solve this simple problem. I had given you the same beam in the previous video also. I had given you the beam, but I have not given you the loads. I told you to develop the stiffness matrix, okay, and I gave you another problem for which I told you to develop the stiffness matrix. You try to solve it by yourself. Now what I'll do is, whatever the stiffness matrix that I developed for the previous problem, the same beam or the same continuous beam I'm taking, and I'm applying some loads, and I'm trying to define or I'm trying to analyze this given beam, continuous beam. Okay, now let us look at this continuous beam. So this is having two spans. The span AB is 4 meters, span BC is 6 meter. The flexural rigidity is EI, and AB is loaded by a concentrated load at the center, which is 24 kilonewton. Now BC is loaded by a UDL of 4 kilonewton per meter, right? So this is what your given beam is. For this you need to analyze. So when I tell you to analyze, what you do is that you calculate what is your moments. So you need to calculate MAB, MBA, MBC and MCB. Okay, so first what you do, I'll quickly explain you what the stiffness matrix is and how we develop the stiffness matrix. So what is stiffness matrix? We need to apply, or we need to assign the coordinates at the kinematic intimacies. First we need to determine the kinematic intimacies. At both the kinematic intimacy points we need to apply the coordinates, and at those coordinates we need to apply the unit rotation, right? So by applying the unit rotation, we are going to calculate what is the force that is created, right? So those forces will be representing you the stiffness values. Now let us do the first thing. What we do is that we determine what is kinematic intimacy. So this is theta B and theta C. So as we know, the kinematic intimacy exists as theta B and theta C. So first I'll take this beam and I'll apply the unit rotation at joint B, and I'll determine how much is the moment that are created because of the application of unit rotation, right? So you already know, because of application of unit rotation for member BC, the force or the moment that is exerted here is 4EI divided by 6. Okay, now one more thing you need to remember. If rotation is there, if you want to create rotation, you have to apply the moment. If you want to create the translation, you have to apply the force. You remember that, right? So now my displacement that is taking place is rotation. So if there has to be a rotation, we have to apply the moment itself. Okay, now you try to understand, whenever I use word force, it basically represents the moment or both force. Okay, right. So if you want to create a rotation here, we need to apply a force. And how much force I have to apply here? 4EI divided by 6. Because of application of 4EI by 6, the far end joint will be subjected to 2EI by 6. Okay, now we have determined what is the force that are created or the moments that are created because of the unit rotation in member BC. Now similarly, if I am applying the unit rotation at this joint, this member will also undergo the unit rotation. So the unit rotation, because of here, applying here, the forces that are created are 4EI by 4 at the near end, and at the far end we have 2EI by 4. Now this completes the forces that are created because of the unit rotation at the coordinate 1. Okay, I had already explained this in the previous video also. Okay, now let us go to second coordinate. Second coordinate is C joint. At the C joint, I am applying the unit rotation. So the force that is required, or the moment that is required to create this unit rotation, is 4EI by 6 at the near end, and at the far end it will generate 2EI by 6, right? So this is what the forces that are generated because of application of unit rotation at the first and second coordinate. Okay, once this is completed, next what we do is we develop the stiffness matrix. To develop the stiffness matrix, what I told you to do, you need to determine all the forces that are exerted at the first coordinate because of application of unit rotation at the first coordinate. Okay, so let us call this as K11, K12, K21 and K22. Let us first see what is K11. What is K11? K11, we have to go over here, right? So this is the force that is created because of application of unit rotation at this joint, at the first coordinate itself. So this is called K11. Now we have two forces here, both are clockwise, both are positive, so add these two. So 4EI by 6 plus of 4EI by 4. So I have taken the EI separately or common. So this is what left over. 4 by 4 plus of 4 by 6 will represent the K11. Okay, now when K11 is sorted, now let us write the K21. What is K21? K21 is the force that is created because of the unit rotation at the first coordinate. So this is your first coordinate. Because of application of unit rotation at the first coordinate, how much is the force that is created here? It is 2EI by 6. So 2EI by 6, EI as I have taken it as common. Okay, now going to next diagram. So now in this figure we are applying the unit rotation at the far end. Okay, so at the second coordinate, right? So at the second coordinate, if I am applying the unit rotation, the force that is created is 4ei by 6. So now this is your K22. What is K22? We are determining the force by applying the unit rotation at the second coordinate itself, right? So the force at the second coordinate by applying the unit rotation at the second coordinate is representing the K22, which is 4ei by 6. So K22 is 4ei by 6. Now let us go here. So what is K12? K12 is representing the force in the first coordinate. This is your first coordinate, right? The force in the first coordinate because of the unit rotation at the second coordinate is 2ai by 6. 2ai by 6 is written. So this I have already explained in the previous video, but still I tried to explain it one more time. Okay. So once you develop the stiffness matrix, next is to develop the force matrix. Okay. So we know that we have these external loads, but we do not know how much is exactly the moment that is created. So first what we do is that we calculate the fixed end moments, which are arbitrary moments, right? So let us determine the fixed end moments for this. So 24 into 4 divided by 8 will give you the fixed end moment as this is at center. So this will be WL by 8, WL by 8. Now this will be WL square by 12, WL square by 12. Now I have determined the fixed end moments, right? So once you develop the fixed end moment, what you need to do is you have to go to first and second coordinate. What is my first coordinate? Joint B is my first coordinate, joint C is my second coordinate. There you have to take the sum of fixed end moments. Let us take the sum of fixed end moment at this joint. What is the sum of fixed end moments? 12 minus 12, which is equals to 0. Now similarly we will go to joint C. At this joint the fixed end moment is how much? 12, right? So at the first coordinate the sum of fixed end moment is equals to 0. At the second coordinate the sum of fixed end moment is 12. Now these are your fixed end moments. So that's why what I do is that I apply negative symbol to this, right? So this force matrix, so whatever this force matrix is there, so this force matrix should be applied with negative value. Okay, I have applied the negative value. Now we know that this is our equation where force matrix is equals to K multiplied by which is stiffness matrix multiplied by displacement matrix. So if I have to rewrite it, it will become like this. So displacement matrix will be equals to force matrix divided by K matrix, or we can say K inverse of matrix multiplied by force matrix. So we already know what is K. Okay, so K we have already determined. We already know what is force matrix. Now we have to calculate how much is inverse of K. Okay, so inverse of K, you already know how to calculate the inverse of K in your matrices. So what I will do is you can either calculate it manually or you can calculate in your calculator also. Okay, so there is an option, you try to search in it how to solve the matrices. You can multiply the matrix, you can calculate the determinant, you can calculate the inverse, everything you can do in the calculator itself. Okay, so there is an option of storing 3 matrices in your calculator. Okay, so those 3 matrices can be multiplied, can be calculated determinant, or you can do anything with that, okay, in your calculator. So I'll try to explain, you try to explore your calculator by yourself. If you don't get to understand, what I'll do is I'll make a separate video of explaining you how to solve these matrices in your calculator. Okay, I'll do it separately. Okay, now this is your K matrix. So I have taken the inverse of this K matrix and this is what the matrix I get. Now I'll multiply with the force matrix. This is my force matrix, 0 and minus 12, as you know. So after multiplying these two matrices, I got to know what is displacement. Now displacement matrix, what is displacement matrix? There are two displacements that are taking place, theta B and theta C. So whatever displacement is there, I have substituted here. So theta B and theta C. This EI was 1 by EI, so I sent it to this side, it will become EI multiplied by theta B by theta C will be equals to this matrix. Okay, so in this matrix you already know, I don't have to explain. EI theta B is equals to 4, EI theta C is equals to minus 20. So I have calculated EI theta B and EI theta C. Now let us take a quick recap of what we used to do in slope deflection equation. In slope deflection equation we used to write set of equations, right? So MAB, MBA, MBC and all those equations. So for example, for this given problem we used to write how many equations? We used to write 4 equations. And how many equilibrium equations we used to develop? 2 equilibrium equation. One is summation of moments at B is equal to 0 and summation of moment at C equal to 0. MAB plus MBA plus MBC equal to 0 and MCB equal to 0. 2 equations developed, 2 unknowns. What are the 2 unknowns you used to have? You used to have the EI theta B and EI theta C. That is what I told. Matrix method helps you solve the equations, whatever the equations are there, the unknowns you can calculate from those equations. Okay, so that is what we have done. We have calculated EI theta B and EI theta C. So once you solve these 2 values, now the next thing is to apply all these unknown values in the slope deflection equation. All of you remember the slope deflection equation, right? So I am just quickly going to explain you what is MAB. MAB is equals to MFAB plus of 2 EI by L into bracket 2 theta A plus theta B. As we do not have any delta translation, so delta has been neglected. So now going to this beam, as you know, theta A is equals to 0. I have cancelled it out. So what is left over? MAB plus of 2 EI theta B by 4, right? So 4 being the length of the member AB. Okay, substitute the value of MFAB and solve MAB. MAB is equals to minus 10 kilonewton meter, right? So similarly you can solve for MBA. What is MBA? MFAB plus of 4 EI theta B divided by L. L is 4 meter. Substitute all the values and determine BA. Now BC can be also calculated and CB is also calculated. But can you tell me what will be the value of CB without solving this? Yes, it is very easy because this is a pin joint. At the pin joint the moment will be equal to 0. So MCB is equals to 0. Okay, but still you try to solve it by the equation also. Write the equation of MCB, substitute these unknown values EI theta B and EI theta C and solve and see how much is the moment that you get at CB. Okay, right. So this is how we have solved this problem. If you find any difficulty, you can comment in the comment section or you can ask me in the Google Classroom. Okay, we will solve more problem on this. Okay, thank you.